This is the first of several videos that are going to explain this topic of goodness of fit. And this video is really going to be a focus on concepts. So the first concept is, what the heck do we mean by goodness of fit? And so we're going to think about goodness of the fit in the context of these three plots. And these three plots are all based on a linear model. So we got a y variable and an x variable. And our linear model is going to say that the expected value of yi, and we can represent that as mu I, is going to be equal to alpha plus beta, which is a slope, times xi. So that's going to give us a nice linear model like that. So that's how we get our expected values. And then our observations are scattered around that line of expectation. Where those observations come from, they're deemed to come from a normal distribution with mean mu I, and to use JAG's notation, we'll have it parameterized by precision. So that's going to be our model. So the question is, how well do the data fit this model? And I would argue that this is actually a pretty good model, a pretty well fit model. Now, someone might look at this and say, come on, get serious. Look at all this scatter. That's a really bad model. But my argument would be that I'm thinking about goodness of fit in a particular way. And the way I'm thinking about goodness of fit is, are the observations, are what we see here, are they consistent with a model that's really got kind of this two-phase approach that we saw earlier when we talked about this notion of generalized linear models? Was that, first of all, we've got the expected value, mu I, that is determined without variability as a linear function of the independent variable. And then our individual observations arise as single random draws from a normal distribution with that mean and that level of precision. And so, notwithstanding the fact that, yeah, there's a heck of a lot of scatter here, these data are consistent with this particular model. Now, it's going to be a different situation when we look at panel B. Because I would argue that this model here is not consistent with the data. Because this model here assumes a linear relationship. It assumes a linear relationship, but when I look at the data, I don't see a linear relationship. What I see is a curvilinear relationship. So this is not a well-fit model. Similarly, if I go over here and look at panel C, there is my line of best fit, but I would argue that this is not a particularly well-fit model either. And the reason is that when I think about how these observations arise, they're deemed to arise from a normal distribution with some mean mu I and some precision tau. But what we assume is that this value of tau, this metric of variability, is constant irrespective of the value of x. And that's not what we're seeing here, because we're seeing at small values of x, we've got relatively little amounts of variability. In other words, we've got fairly precise data, whereas as x is larger, the observations appear to be coming from a normal distribution with a lower level of precision. So that's just kind of the concept of what I mean about goodness of fit. Now what I want to do is come back to our example with birds and our population size. And so the way we're going to set up our JAGS program is that for each chain, we're going to get 9,000 iterations. And think of what happens in each iteration. In each iteration, we're going to get a value of alpha, we're going to get a value of beta, and we're going to get a value of tau. And our model we saw is going to assume that mu I, remember I is equal from 1 to 16 because we got 16 different years, that mu I is equal to alpha plus beta times year I. And so if we look at iteration 2000, we get our values of alpha, beta, and tau for year 2000. We generate this value of mu I. There's mu I, those solid dots. There's our solid dots. There's our line of best fit. But there's something else we can now do. We can now generate new values, and this is really the key. I'm going to generate a series of new values called y new I. Y new I. And how am I going to get them? They're going to be assumed to arise from a normal distribution with some mean mu I and precision tau. So we've got mu I, which comes from here, and tau, which comes from there. And so we're going to get these values of nu I. There they are as these squares. Like that. And then, as I say, we're going to have these 9,000 iterations. So in the next iteration, we'll get a different value for alpha, a different value for beta, and a different value for tau. And we'll get a different series of values for mu I. So if you look at this line here, it's slightly different from this line here. And then we're also, as before, going to get a whole series of y new I's. There they are. Like that. And then we're going to move on to iteration 2002. Repeat the process. New values of alpha, beta, and tau. Consequently, we'll have different values of mu I. We'll have a slightly different slope. And then we'll generate a series of y new I values like this. There they are. So that's the process. So what does any of this have to do with goodness of fit? Well, here are, at each iteration, we've got our values of y new I. And they're going to vary. They're going to differ from one iteration to another. But we've also got these values of pop size. These are the observed values of population size. They're shown as open circles, and they're going to be constant throughout all these iterations because this is just our data. So the whole idea of these goodness of fit tests is that we can ask the question, well, how good is the fit between our model line and our observed values of pop size, shown as these open circles? And we can ask ourselves, how good is the fit between these newly generated values of y new I and a particular model? And the whole concept of these goodness of fit tests is that if we have a well-fitted model, if our model fits well, then the pattern of deviations for the observed values should be very similar to the pattern of the deviations of the newly generated values. And that's going to form the basis of our goodness of fit tests.